Okay, so last time we had figured out the phase diagram of this model. Okay, so from this duality we can argue that the transition has to be at g equal to 1. So if you remember, what we had was there were these two different ways of writing this model in terms of the z's, sigma z's, or in terms of these new variables we introduced. Let's call them the mu. Okay. And we said that over here you have the broken symmetry state. Okay, it's the all up or all down. And another way to characterize this is to say that there's an expectation value to this operator. So there's condensation of these spin flips, and that gives you an expectation value to this operator, which is actually odd under the symmetry, so you break the symmetry. Okay, that's another way to talk about it. And we had described what this spectrum over here was. There were these excitations, which are basically the spin flips, and there was an energy gap to the ground state, right? So these excitations were created by basically the spin flip operator sigma z. And by duality, what you expect is that on this side as well, there are similar kind of excitations, and we figured out what those were. Those were the domain walls. So we had similar kind of spectrum created by mu z in this case, the domain wall operator. So mu z was, this was the non-local operator. Okay, which created this domain wall. And so now we want to describe the transition, right? So you can see that if you want to describe the transition, the problem with describing the transition, so one way is to describe it with the Landau-Ginzburg theory. There's a symmetry that's broken, so you can write down a Landau-Ginzburg theory and say that that particle condenses, and you know, that's certainly one framework to discuss this in, except it turns out that those variables are very strongly interacting. Okay, it's hard to make progress there to do anything quantitative. So instead, what you'd like ideally is to find some variables which will reduce to these excitations on the right hand side, simply the spin flips. That's really the simple excitations on the right. But if you come to this part of the phase diagram, they should kind of morph into these domain wall excitations. Okay, and if you can find a single set of variables like that, you'll be able to describe this transition very easily, right? Because the transition involves these spin flips coming and condensing. It also involves these domain walls condensing. Okay, you can think of it in either way, and the question is, are there variables that can smoothly interpolate between something that looks like this and something that looks like that? Okay, so so in fact we can find such variables. So think of the following thing, which is a product of the sigma z operator and the mu z operator. Okay. Okay, so so let me call this chi. Okay, so this thing actually has the property we require, because imagine I take this operator and set deep over here in the ordered phase. Okay, so now essentially your sigma z has acquired an expectation value. You can think of the sigma z as being just some number. So you can forget about this part of the operator. It's just some number, and it's just this mu z, which is the operator that creates domain walls, which is what we wanted over here. Okay, and by duality, if you think of this as sigma z being having some expectation value, by duality you can think of this part of the phase diagram within quotes as having condensed the domain walls. Okay, on this side you have a lot of domain walls in your system. It's kind of like they've condensed. You can think of this as acquiring an expectation value. So if you look at this operator there, you can think of this as just a number. It reduces to the z operator, which is just the spin flip away. Okay. So this composite operator is really what you want, which can describe both sides of the phase diagram. In the limiting cases, it really shows up and it reduces to the operators that you want to create the excitations that you know occur at the ends of the spectrum. Okay, so it turns out that these are actually fermion operators. So this is the bose-fermi duality. If I think of the spins as bosons, this is a mapping to fermions, and we'll see why we are calling them fermions in a second. You can also define a tilde. There are two of these fermions at every site. Use the sigma y. Okay, and you can define a complex fermion if you like, which is the sum of these. Okay, let me call that C dagger, and C similarly. And if these are fermions, we expect them to satisfy the usual anti-commutation relations. So if I take a pair of fermions on different sites or same site, the anti-commutator is that, and if they are both C's, then it's just 0. Okay, so you can check. Well, they commute on different sites, right? So you can think of them as, there's a two-level system. You can think of it as hardcore bosons, and the operator that creates a boson on one site commutes with the one that creates it on a different site.
If I just think about
sigma z's, yeah. Yeah, whereas these operators are not like that. So, so for example, the thing that's a little easy, this is equivalent to saying that chi I squared and chi tilde squared is unity, and chi I, take a pair of these, it could be on different sites. Okay, and similarly for the tildes and the mixed ones. Okay, so these are easy to verify. For example, if I take this pair, I take a pair of them. So this is like the Z Pauli operator, and the mu's simply give you x's. So let me use the shorthand for the Paulis, the sigma operators. And then I take another one of these at a different site. Okay, and you can see what they have in common is, and what does not commute is a Z and an X, right? And these anti-commute. So for example, you can verify this relation. These are kind of trivial. And it turns out that this set is the same as requiring the usual anti-commutation relations for fermions. Okay, so these are really Majorana fermions. Okay, it's a good exercise to check that these satisfy these anti-commutation relations, which is equivalent to the more familiar one for complex fermions. Okay, just a little bit of algebra there. Okay, so now we'd like to write the Hamiltonian in terms of these new variables. Okay, so let me just write down the answer, and so it takes on a very simple form. So it's sum over all sites. Okay, so if you just look at these terms over here, transcribe the sigma x into fermions, that's kind of easy actually. If you look at the product of these two operators, you take the product, these mu's will cancel, and the sigma z and sigma y will combine into an x. right. So that's really what you want. You want the product, but there's a factor of I. That's the factor of I over here. Okay, and for this is a little more complicated, but you can work it out. So you want the product of the Z operators, but they're on different sites. Okay, so so if you were to simply take the product of the fermions on two neighboring sites, then you'll get an additional sigma x coming from the string. Okay, so instead what you do is you take one of these, so you get a Z times x, and then you take the other Majorana fermion over here, you take the y, so you combine that, you get a Z and a Z, which is really this product over here. You take a chi and a chi tilde on the neighboring sites. Okay, so this is the Hamiltonian, and the most important thing to realize is that this is free. Okay, so this is reduced to the one problem we can actually solve, which is free particles, right. Okay, and so these are really the correct variables, and this is a reflection of the argument I gave before. These variables reduce to what you want deep inside the phases. Okay, so let's draw a picture of this Hamiltonian. So every site is composed of these two so there's a chi, say j, and chi tilde j. Is that what? No, I think I want a tilde on the left. Okay, so this term over here is this kind of a bond. Okay, these are the hopping terms, if you like, and this term over here, chi tilde chi, is this kind of a, right. So the thing that's special at, yeah, question.
I understand this because it looks like Hilbert space is double. Because originally you're going to have the latent spins, but now you include the gauge field and the original spins.
There are no gauge fields.
I mean the mu spins.
So the mu's can be written in terms of the sigmas. Okay, so maybe I should write those explicitly. Let me remind you what the mu spins are, right. The mu is just a product, it's just a shorthand. You can, if you want, you don't have to if you give me a if you give me a sigma configuration, I can tell you exactly what the mu's are. So it's not independent, it's just a rewriting of the original variables of the system, and it's a faithful representation of your problem. Yeah. Yeah, there are no additional fields being introduced. So these are simply some non-local fields in terms of the original spins. It's like there's a Z and a product of X's. That's just the Jordan-Wigner string. So if people are familiar with that, this is the usual Jordan-Wigner. Okay, where you write your fermion as some C dagger as some sigma plus times some string operator, which is the product of these sigma X's. Okay, so it's the same story, I've just introduced it in a different way. Other questions? Okay, so we said that the critical point is at g equal to 1. Okay, so what happens at g equal to 1? Well, right now these two bonds are of different strength. This is strength g and this is 1. But if you're exactly at g equal to 1, this becomes a very simple problem where all of these couplings are exactly the same strength. Okay, so let's work in that limit. So you can just think of it as a different model, if you like, which has exactly one Majorana fermion per site. Let's call them the eta fermions. Okay, so eta 2j minus 1 will be our chi tilde at j, and eta at 2j will simply be chi at j. Okay, so I just double the number of sites and have a single Majorana fermion at every site. Okay, so so in this representation, the j equal to 1 Hamiltonian is extremely simple. It's just summed over all sites, eta r plus 1. Okay, so at criticality you have a translationally invariant system written in terms of these etas, and we'll see why this is critical, why this is gapless, simply by solving this Hamiltonian. Okay, so some questions that you can ask is, now that you have a very simple description of this problem in terms of fermions, okay, so what is the critical point in terms of fermions? Okay, what are the two phases? Okay, so we know that the Ising model had two phases that should correspond to two phases of the fermions, and a more quantitative version of this, what is the critical point, is can we find exponents? Okay, so we'll answer all of these very quickly. So first we'll take that theory that we had and try to solve it. Okay, it's a free theory. It's translationally invariant. I just have to find a basis where it looks, simply looks like number operator times an energy. The basis that sort of it's like normal modes. The normal mode for that, of course, is use Fourier transform to solve that. So you write this in terms of some Fourier fields. Okay, so let's call it eta q. And I won't go through the details. It's the usual tight binding kind of argument, except these are Majorana fermions. So at the end of the day, you get the energy spectrum is sine q, chi q, eta q. Okay, something that looks like that. Okay, for q greater than 0, and if you plot this function, it simply looks like that, right? Okay, so q equal to pi and q equal to 0, it's gapless. Okay, this is all measured in units of j. So you have modes that go down to 0 energy, so it's gapless, and they occur at these 2 points in momentum space. Okay, so that's the nature of this critical theory. If you're only interested in low energy phenomena, which is what we are interested in for these critical phenomena, you can forget about this entire dispersion and simply focus on the low energy degrees of freedom. Okay, so in other words, you only want to focus on modes that have wave vectors close to 0. That's the usual sort of long wavelength mode. But actually there's another mode that's low in energy, which is wave vector pi. So this really corresponds to things varying on this scale of 1 lattice spacing in that eta thing, but 1 lattice spacing there is really the difference between something happening within the site and between the sites. Okay, so both of those fields are very important. So let me sort of write down a continuum description which is basically captures all of the physics of this problem. At long distances, there's one field eta 1 which is going to be centered near q equal to 0, and there's another field which is rapidly changing sign from side to side. That's really this part, and there's another field eta 2, and both of these are going to be assumed to be very slowly varying. Okay, the wave vectors contained in eta 1 and eta 2 are very small, all of the significant lattice scale physics is contained in the fact that this varies rapidly from site to site. Okay, so we'll use this and try to derive an effective theory for these slowly varying fields. Okay, so this is really how you derive a field theory. Right? So we had a model defined on a lattice, and we want to take the continuum limit. We want to forget about the physics at the scale of a lattice, only look at long distance physics. For that, the first thing you need to do is to isolate the slowly varying fields which contribute to low energy physics. They are slowly varying in space, so you can sort of ignore the lattice level variation and simply write down a field theory. Okay. Okay, so let's do that. We've identified the fields. So now what we want to do is to write down, take this Hamiltonian that we had over here, this very simple one, and write that down in terms of the slowly varying fields. Okay, and you'll see that what we get, the continuum theory, is going to look like a Dirac equation. Okay, that's how the Dirac equation comes out over here, the one-dimensional Dirac equation. But the fields involved will be real fields, so it will be the Majorana Dirac equation, and we'll see what these, the two phases correspond to, and different details of the critical point. Most of them can be read off from this simple theory. Okay, so I want to substitute that slowly varying field into my Hamiltonian, which was someone called J. What was it, R? Okay, so let's do this a little carefully. So we'll expand. So it's eta 1. Right. So this is the adjacent site. So I pulled out a minus sign from this. Okay, so you take the products and expand. There are two kinds of products. The first is a product of slowly varying fields. Okay, there's a minus sign over here because this had a relative minus compared to this one. It's the next site over. Then there's a cross term which has minus 1 to the r, this pair, and minus 1 to the r, this pair. Okay, that cross term you can neglect, because when you do the sum on r, you have one factor that's varying very rapidly, minus 1 to the r. The product of these two fields is very slowly varying. Okay, so from side to side it's not changing very much, so those will cancel out. Do the sum on r, they'll just give you 0. Okay, so the only term that remains after the sum on r is the product of the slowly varying fields. It looks like this. Well, these fields are not really varying very much. I can think of them as fields rather than lattice scale objects. So r plus 1 is simply the field at r plus the derivative. Okay, you do a Taylor expansion. Okay, so then from that you get, I can think of this now as an integral. There's some energy scale Vf. The sum becomes an integral. So this eta 1, you get dx eta 1. There's a constant term which is eta 1 squared, but that will cancel off against the eta 2 squared term, so don't worry about that. Okay, you just get this. Okay, so this actually looks like a Dirac equation for massless fields. So what you can do is you can define a two-component field. Let's call it psi. So my psi will be eta 1, eta 2. This is just psi transpose sigma z. So this sigma z has nothing to do with the spin sigma z. It's just a Pauli matrix in this 2 by 2 matrix, in this 2 by 2 basis. So it looks like psi, psi bar, some Pauli matrix, dx psi. Okay, this is just the Hamiltonian of a Dirac field. But these psis are really real fields. So if you look at the spectrum in these new variables, you have energy and momentum, and you have a right mover and a left mover. Okay, this guy is moving right. This derivative gives you a positive energy for wave vectors to the right and positive k and negative k. So this is the spectrum. So this is a massless Majorana mode. Yeah. Are you talking about here? Or? Yeah. So so you have eta 1 squared, which is 1. If you like, or it's there are two Fermi fields at the same point. Yeah, it's just some constant term that you can neglect. Yeah, you can go back and see what it is in terms of the original fermions. It's yeah, so we'll see there is a term that is non-trivial, but it involves eta 1 and eta 2, and those will actually open a mass gap. Yeah, other questions? Okay, so that is the critical theory. So now what if you move off criticality? If you move away from this g equal to 1, what is the term that tunes you away from this point? Okay, and obviously it has to open a gap. The Ising model is gapped away from the critical point. We saw that you had the spin flip or domain wall excitations, but they always came with an energy gap which closed only at the critical point. Okay, so you have to reproduce the fact that you get an energy gap. And those come from this g term, right? If g is different from 1, that's when you get this energy gap. And so essentially the term you need to add, when you move away from g equal to 1, is something that tells you that this bond is different from this bond. Okay, so if g is different from 1, I want that the bonds are modulated in an opposite fashion, whether r is even or r is odd. Okay, so essentially this is the term that tunes you away from criticality, and we can try to put in the slow fields and see what this means. Okay, so we make this expansion in terms of the slow fields, eta 1 and eta 2, and obviously what's going to happen is that now you only want the cross term. Okay, the cross term is the one that's going to save you from this minus 1 to the r. Okay, so you put in this term and ask what it gives you in the field theory. And it gives you an additional term g minus 1 times, actually let me first do it over here. Okay, you'll get dx eta 1 eta 2, okay, with a factor of I. Okay, so now that's because in this kind of a product, you have an overall minus 1 to the r and you want this cross term. Okay, and this turns out to be just a mass term. When you write it in terms of these two component fields, it looks like psi transpose sigma y psi. Okay, and the coefficient is g minus 1. Okay, so this coefficient, this Pauli matrix anticommutes with this one, so it's like the mass matrix in the Dirac equation. Okay, so the energy dispersion will go from being linear like this. So now you add a mass term, and let me draw it in miniature. There's and now there's a mass which is essentially this g minus 1. Okay, and the transition in terms of these fermions is dependent on the sign of the mass. Okay, so you have a mass which can either be positive or negative, and those correspond to the two phases of your system. Okay, so in the field theory, it looks these two phases have very democratic within the field theory. You're just changing the sign of the mass, and since this is a real parameter, it has to go to 0 somewhere, and that's what gives you the critical point. Okay, so immediately you can read off something. You can read off a critical exponent. Okay, so you know that if you have a massive particle, there's a certain length scale which is defined in a relativistic theory. If I tell you there's a mass m, you can derive a scale from a length scale from that mass. It's like the Compton wavelength. So you can, for example, say that if you're at a, have a mass m which is g minus 1, there's a length scale, let me call that psi, let me put it up here. Okay, so there's a length scale psi which is essentially the inverse of that mass. Okay, so if you like, mass is equivalent to energy, and if you have an energy you can get a time scale, you can use the speed of light to convert that back into a length scale. Okay, so basically there's a length scale which is the inverse of the mass. Okay, but this is actually a critical exponent. It tells you how this the correlation length diverges as I approach the critical point. Okay, and this just told you that this critical exponent nu is just 1. Okay, just the fact that it's free fermions acquiring a mass immediately tells you this critical exponent. Okay, so it's very powerful. You really solved this critical theory. It's very hard to get this exponent if you were to just look at it in terms of a theory of an order parameter field, but in terms of fermions it's trivial. Okay, there are other exponents that are a little hard to get in terms of fermions. For example, the correlation function between the sigma z's at the critical point, you need some more tricks to get that, but in principle even that is doable. Okay, so this gives you a description of the critical theory. It tells you the what the critical exponents are. Yeah. Say that again. Yeah. Yeah. Okay. So so this Hamiltonian is very simple at j equal to 1.
That's right. But there's no g squared in the original Hamiltonian. You're saying those would be coming from the mixing terms between the. Okay, let me ask it another way. The Hamiltonian written in terms of the chi's you said was this is also a free fermion Hamiltonian.
This is a free fermion Hamiltonian. Yeah.
Couldn't I solve that exactly?
Yeah.
Get an answer.
You get the same answer. Yeah. That's right. Yeah, you can solve this exactly. That's what. So instead of the sign, you have some structure that's a little more complicated than just this. You get a 2 by 2 matrix. So it looks like the energy looks like sine squared k plus g minus 1 squared, roughly speaking, square root of that. Yeah.
For example, when g is very small, for example, when g is 0, then the two Majorana mode and the boundary are localized, right?
Yeah.
Why
Good.
can't I say that in the
Yeah, that's a good. Yeah. So let's get to this question, which is, what are these two phases in terms of the fermions, right? So the field theory is not very good for that because the field theory kind of has thrown away some of the lattice physics that actually distinguishes those two phases. So instead, let me use this representation over here in terms of these chi fermions. So what is the distinction between these two phases? Well, let me look like you just said in the large g and small g limit. Okay, so g much larger than 1. So basically what I have then is that these couplings are strong. So I have these sites and they form kind of these pairs within the site and they simply form a gap state, right? So the g much greater than 1 is sort of a gapped Fermi and even at the edge you see nothing funny is happening. It's just a trivial you can call it a trivial superconductor or a trivial insulator of these Majorana fermions. But if you go to the opposite limit where g is much less than 1, okay, so now the dominant couplings are the ones between the sites, right? So these blocks I'm drawing are the sites j. They have two Majorana fermions in them, and now you see that there's one Majorana fermion left off over here and over here. Okay, so this is the topological phase, if you like. Okay, the Kitaev Majorana chain. Okay, and this will have Majorana 0 modes. If you just examine the spectrum of this lattice model with a finite boundary, you'll have Majorana 0 modes on the left and on the right. Okay, and those 0 modes are robust as long as the size of the system is very large. There's a gap in the bulk of the system, so they do not talk to one another. Okay, so here's an example where in the original spin variables you had an ordered phase and a disordered phase. You broke a symmetry. You then transformed it into these fermions, and in terms of the fermions, the two phases correspond to a topological and a trivial phase. That is the distinction, and the transition corresponds to a phase transition between a topological phase and a trivial phase, typically for fermions that proceeds through some sort of Dirac kind of criticality. It happens for quantum Hall, it happens over here as well. This is here because you have no number conservation, it's actually a Majorana critical point. Yeah.
Question. If I go to dimension 1 plus epsilon, when one of the phases will be ordered thanks to the ordered phase, is it still topological condition?
So in 1 plus 1D, this is 0 temperature, right? Are you thinking about finite temperature? Or?
No, I'm talking about dimension. 0 temperature transition, but dimension will be 1 plus epsilon. So
yeah.
Will transition still remains topological?
Yeah, but it's probably not dual to the 1 plus epsilon, the Friday the 4th theory in 1 plus epsilon. The duality may break down. I'm not very clear how to do this in some fractional dimension. Maybe you can, it's the usual problem of Dirac fermions in fractional dimension. So you have to find gamma matrices, 1 plus epsilon gamma matrices, or 2 plus epsilon gamma matrices. How do you do that? So there is some ambiguity over there.
Maybe on a more simple way, what I'm asking is this. There's a transition in which you don't have actual long-range order on any side of
Right.
the transition.
Right.
What if you consider similar transition when you do have long-range order? Can you simultaneously with development of long-range order also have change of topology?
Aha.
You do have long-range order.
No, he's saying in terms of fermion variables you don't, right? Is that what you mean?
No, all spins are up in long-range order.
He's talking in terms of the vertical.
It's Ising model.
And this is Ising. This is Ising. So whether it's ferromagnet or antiferromagnet, you get long range order. This is just Ising symmetry. It's not XY or Heisenberg. Okay. Any other question? Okay. So yeah. So we discussed this. So one question you can ask is, why don't I see this distinction in the field theory? Right. Field theory seems to treat these two democratically. And the reason is that in order to, the physics really here, the distinction between these two appears because you draw these boxes, right? You say that this pair of things are in a site, this pair is the bond, and you can only cut the system with an integer number of sites. You can only cut it in between the sites, not in the middle of a site, right? So this distinction has to be built into the field theory if you wanted to tell them apart. So you need some sort of regulator. I have not put in a regulator, but if you properly put in a regulator, you can see that one side is topological and the other one is not. It's a bit like having a background Chern-Simons term. So on one side you get the right, you get 0 and 1 for the quantum Hall effect. Something similar can be done over here by adding some background fermion fields that are already gapped and give you some background term. Okay, but sort of a fine point. Okay, so let's see, what else do I want to say about this? Yeah. So one interesting question you can ask, someone asked me when I gave this talk a while back, is let me think of the theory which does not have mass, right? The massless theory, which is the critical theory. Okay, so that theory actually has what's known as a chiral symmetry. Okay, so if I just look at this action over here, there's no coupling between eta 1 and eta 2. Okay, eta 1 talks to eta 1, eta 2 talks to eta 2. So what I could do, of course I could change the sign of both eta 1 and eta 2. That's an invariance of this theory. That's simply the fermion parity. You cannot have an odd number of fermions in the Hamiltonian, but you can also do something different for this massless theory. You can just change the sign of eta 2 and not change that of eta 1. Okay, so that's called a chiral symmetry. I'm kind of running out of board space over here. Oh, I can use the whiteboard. Is there a marker somewhere? Okay, so the question is, what does this chiral symmetry correspond to physically, right? Okay, let me just erase this, that's fine. Okay, so this is a symmetry of the critical point, and you can ask, what does this transformation correspond to? Okay, very simple transformation in terms of fermions, just change the sign of fermion, of one of the fermions, but not the other. Okay, so any suggestion what this corresponds to in the original model?
Particle
What is particle hole for the spins? Okay, so you can get a clue from the fact that if I were to move off the critical point, if I go into one of the phases, I have this coupling term eta 1, eta 2, and now I do not have the chiral symmetry anymore. In fact, if I take this symmetry and implement it on this mass term, it changes sign. Okay, so in other words, this is a symmetry that is obtained at the critical point, but if I move off, the symmetry takes me to the opposite side of the phase diagram. Okay, so this is really just duality. Okay, this sigma to mu duality that we talked about, in terms of the fermions, is implemented in this very simple way. Okay, and if you think about it, what is it doing? Well, we said this eta 2 field is the one that changes sign from side to side. It's the fast moving, it's the part of this, the -1 to the r field. So really what this is just translation by a half unit. Okay, so if I have this theory in terms of these Majorana fermions, this is the physical translation. You move it all the way here, but you can imagine a translation where you just move it this much. Okay, that's a transformation. There's no reason for the theory to be invariant under that, but what you do is you basically exchange the role of chi and chi tilde, and you move things over. Okay, and if you see what that does to this term in the Hamiltonian, it basically switches these two terms around. Okay, so duality in terms of fermions is really trivial. It's just this sort of half translation. Okay, and that also tells you, it's also consistent with this picture. The only distinction between these two phases is the fact that we define the sides to be here. If I define the sides to be this pair, you would call this topological and this one trivial. Okay, so the half translation will exchange the trivial and topological phases, the thing that sort of mixes up what is called the side and what is called the bond. Okay, so that's sort of an interesting observation about these the fermion variables. Okay, how much time do I have?
10 minutes.
Okay, good. So so this was all for the 1 + 1 dimensional system. Okay, so you can ask, how does this relate to duality in higher dimensions? Okay, where so here you can do things very explicitly, but once you do that, I think you can get a little more bold and try to sort of generalize this, try to identify the features that allowed all of this to work as it did. Okay, so the first part that we talked about was the self-duality, okay, the sigma to mu transformation. Okay, so what is the physics of this transformation? Yeah, you had a question?
Yeah, so before you go into the higher dimension, so I want to ask, so is that all the duality in one dimension can be understood in a certain way? Say I'm not starting with, say I get a transfer the I model, I say I have some other model with the same symmetry, can I still use the same duality to it?
Yeah, you can. Yeah, you may not be able to make this kind of very exact correspondence, but for example, the properties of the critical point they will be the same as what I just described, because if you add interaction terms, the more generic terms, you can add 4 fermion interactions, for example. You can show all of those are irrelevant at this free fermion fixed point. So the universal, the long distance physics will be the same as what I described.
And then this is the only possible, the only possibility you want possible.
Yeah, for a critical point, yeah, that's right. If you have Ising symmetry. Yeah. So actually one interesting paradox, you can try to think about this. So this transition we talked about is only present if you have Ising symmetry. If I break the Z2 symmetry, let's say I apply a magnetic field along the Z direction, I break the Ising symmetry, you don't have a transition anymore because the symmetry is not present anymore. Okay, so then you can go continuously from here to there. Okay, you lose the symmetry, it's not very surprising, but the interesting question to ask is, what about in the fermion representation? Okay, so we are all told that these phases are different and I didn't need any symmetry to distinguish them. Okay, and I didn't need any symmetry to say that to protect this topological phase, it's simply Majorana 0 modes. Okay, so what goes wrong? So once I put on a magnetic field in that language, in spin language, the effective theory over here should somehow allow me to go from this to that in a continuous way without having a phase transition. They should be the same phase. Okay, and you can ask yourself what goes wrong, why is it that these become the same phase? Okay, and it's an interesting exercise and it's a very important lesson in locality. You'll see why locality is so important, and you know why we kind of assume it to be true when we have physical variables, but those chi's were not really physical variables. They're some mathematical objects we define, and there's no reason why the effective theory that involves them should be local. Okay, and you have to check, and it's really the symmetry that guarantees that locality. Okay, so, or you know, in that particular context. Okay, so the self-duality, why exactly did we get the self-duality between spin flip and domain wall? Okay, so effectively what's happening is that both the spin flip and the domain wall are particles in one dimension. Okay, so they both occur at some point in space, and you know, they both have some sort of Z2 symmetry. Okay, I always create the domain walls in pairs because of the physical symmetry. I always create spin flips in pairs. You know, the Hamiltonian only creates pairs of spin flips, and in fact, you know, just the fact that they are, you know, just these pieces of information, also that they have just short range interactions, you know, local interactions. This allows you to write down a field theory for these, for either of these objects, which takes the same form. Okay, so you have some Z2 symmetry, so you have some scalar field phi that changes sign under this under the symmetry, and you just write down some Landau-Ginzburg theory for that phi. Okay, so you write down something like delta mu phi squared plus some phi squared and phi to the 4th terms and so on. Okay, and that's just dictated by symmetry. I only have the even powers of phi because of the Z2 symmetry. It's some local theory, and this is basically the only thing I can write down. Okay, and if you were to write down something for the domain walls, you would have the same set of arguments giving you something identical. Okay, and so ultimately the physics of this problem, the reason you have this self-duality you know, more deeply is because with these conditions there's basically just one field theory you can write down. Okay, or you know, one you can you're talking about the same kind of objects. Physically they may be different, but they have the same character. Okay, so you know, you can be emboldened by this to try to write down a duality in 2+1 dimensions. Okay, so let's say I have bosons in 2+1 dimensions, and the first thing I need is, if I want to write down a dual theory, I want that my defects, just like over here I had these domain walls, I wanted my defects to be particles. Okay, point objects in 2 dimensions, 2 spatial dimensions. Okay, so obviously a Z2 theory would not work. If you had a Z2 symmetry, you would have domain walls, those would be your defects, but they would be lines in 2 dimensions, right? They would be loops. So they are not described by a position, they are not particles, they can't be described by a field theory. Okay, so instead let's change the symmetry. Let's say I have a U1 symmetry, or if you like it's just O2, there's a rotation symmetry of vectors in a plane. Okay, so this is just the XY model. Okay, so I have sites, I have spins if you like on the sites. This could also be the superconducting phases of some junctions, but let me just think of it as a magnet. They have some XY spin, so the order parameter now is or the spin on every side is parameterized by an angle. Okay, and or you can write it as a complex field, combine these into a complex field, some amplitude and the phase e to the I phi. Okay, so instead of a real field phi, you can have you now have a complex scalar, complex field. Okay, and the usual Landau-Ginzburg theory for a transition, you know, from a trivial phase of these XY magnets, you can think of that as similar to the high temperature phase of a 3-dimensional XY model, or this is the paramagnetic phase of a quantum 2+1 dimensional XY model. I won't write down the macroscopic Hamiltonian, but there are two phases. There's an ordered and disordered phase. Okay, and this transition again you can write down in terms of some Landau-Ginzburg kind of theory. There's some dynamics for this complex field, and then there is some mass term, and when I change the sign of this mass term, roughly speaking, I get condensation of sign. Okay, that's the usual Landau-Ginzburg kind of picture. Okay, but now I can think of a dual theory written not in terms of these spins or bosons, but in terms of the defects. Okay, and the defects here are vortices. Okay, and these are point particles in 2 dimensions. Okay, so again these vortices carry a charge, an integer charge. Okay, so they are like they carry a U1 charge, they carry something that is not Z2 or something discrete, but actually a full integer worth of charge. So these you can also write in terms of a complex field. Let me call that psi vortex. Okay, so at first sight this also looks self-dual. You know, if you write in terms of this complex field, it looks a lot like this one over here. Okay, the question is that really true? So there's one big difference between the 1-dimensional case and this 2-dimensional case. If you look at the interaction between vortices, that's actually not short-ranged. Okay, so these so if you're familiar with this Kostelis-Thouless phenomenon, the interaction between vortices is like that of charges in a plane. Okay, it looks like the 2D Coulomb force. You just look at static vortices, they have like a log potential between them. Okay, so so these are not short-range interacting particles. They don't have the same form as this theory. Okay, so you can remedy that. This interaction is really arising ultimately, like all electromagnetic interactions, it arises because of coupling to a photon. Okay, so if you had coupling to an electromagnetic field, you would be able to mimic this interaction. So in fact the dual theory in terms of vortices, the same theory written in different variables, has a gauge potential in it. Okay, so that's the minimal coupling to a gauge potential, and when that gauge potential fluctuates, that will give you the required long-range interaction between the and then you also have the Maxwell term, which is the electric and magnetic field squared. So you can write it like that as some E squared as B squared, where the electric field is the usual D0A. Maybe I use the vector notation. Okay, just electromagnetism, but in 2+1 dimensions. Okay, so it turns out that this theory actually is dual to this one by these sort of general arguments. Okay, and so the question, yeah. So in 2 plus 1D you are allowed a Chern-Simons term, but you don't have to have it, and in fact this one does not, you don't want that in this particular duality. So this is a boson to boson duality, it doesn't have a Chern-Simons term, and it's kind of very important it does not. So if you make this identification between phases, so there are two phases in this theory, the disordered phase and the ordered one, of course, but there's something different about the ordered phase because this is a continuous symmetry. Okay, so if you're in the ordered phase, it actually has gapless excitations. So previously we did the Ising model, there were no gapless excitations even in the ordered phase, but over here because of the continuous symmetry there's a theorem, Goldstone's theorem, that tells you there must be a gapless Goldstone mode. Okay, and you can ask how is that reproduced in this particular theory, and by the usual duality, when this field is condensed, that's the ordered phase. In this dual side, this dual field is actually gapped. Okay, that describes the same phase. So in fact I can just forget about all these psi v's. The effective theory in the so-called ordered phase, the original ordered phase, is just electromagnetism. Okay, and you can ask, okay, how does that account for the Goldstone mode? We need a gapless mode, but this theory actually has a gapless mode, it's just the photon. Okay, and so then there's an identification between the Goldstone mode, okay, and the photon of this dual theory. Okay, so that turns out that you can only do that in 2 plus 1 dimensions. So in 3 plus 1 dimensions you cannot identify the photon with the Goldstone mode, but in 2 plus 1D these are actually just dual to one another. Okay, so you can have two views of this transition, either as a Bose-Einstein condensation where you get order in the Goldstone mode, or a different transition where in this phase actually the fields are gapped and then they condense, and when they condense they actually Higgs out the photon. Okay, so this disordered phase in this language is simply the Higgs phase. Okay, so order is what's called the Coulomb phase, where you have a photon, and the disordered phase is just the Higgs phase. Okay, where you condense an object that carries gauge charge, you may think that this has a gapless mode because of the Goldstone's theorem, but because it's coupled to this gauge field, two things happen. You lose that gapless mode and you also lose the photon that was previously gapless. Okay, that's the Higgs mechanism in a very simple context, and that can end up giving you, describing this disordered phase that's gapped. Okay, so so maybe that's a little bit heuristic, but you know these sort of general considerations can lead you to this particular duality by matching all of the physics of this, the phases and phase transitions over here. You can match it to this. Okay, so it turns out that this, yeah.
One big difference between the 3D and the 3D cases, you can't actually solve this one, right? So,
yeah.
Do you have an explicit mapping between the two? Is this an exact law or something that's a law?
So you can write down an exact duality on the lattice, but it's going to look very complicated. It's not going to have, you know, if you make this simple over here, it's going to look fairly complicated on this right hand side. So it's not like the 1D case where both, you know, you just got free fermions, something like that. But that is in some sense part of the utility of this mapping. So what it suggests to you is that the phase transition on this side is the same as the phase transition over here. The phase transition over here is very well understood. You cannot solve it exactly, but there's a lot of, this is just a Wilson-Fisher fixed point. There's a lot of numerical studies and stuff like that, epsilon expansion, that looked at this one. But it turned out that this right hand side for a long time was very controversial. It wasn't clear if this theory had a continuous phase transition. Okay, and the epsilon expansion fails for this particular theory. It gives you, predicts a first order transition. And so as a debater, you know, is this really continuous or not? All of the epsilon expansion results held in 4 minus epsilon dimensions, strictly speaking. But then with this duality, it was realized that this could have a continuous transition, and it could be related to this theory which actually had a very simple Wilson-Fisher kind of interpretation, and numerically this seems to work out. So when people simulate this model, they see the critical exponents of this model. They have the same IR fixed point, yeah, as far as we can tell numerically.
Beyond that, we're not saying they're the same. You're saying they're also.
That's right,
all
yeah.
the deformations are the same.
Sorry?
Are we saying all the deformations of both the fixed points are the same as well, or are we saying it's just an IR?
So every deformation of this critical theory, you can find a reflection over here, and yeah, that is actually the easy part, to say that in fact this is simply rewriting the theory in terms of these vortex variables, and you should be able to describe every phase of the model in terms of vortices. It's just your choice that you started with bosons to begin with, or XY spins. So there should be some reflection of all the phases in these variables. They may be very hard to access, and the similar question is for this critical point. There should be some reflection in terms of the vortices. It simply may not be weakly coupled, QED. This is like QED, right? It's a boson coupled to electromagnetism, Kapler's boson. So lattice models are not quite in the weak coupling limit. They start with some finite coupling, but you can very easily find a lattice model in terms of these variables which flows to this fixed point. So we believe it's true even for weak coupling. Okay, so I think I've already run out of time, but in a similar way you could do a bose-fermi duality just like we did before. We have clues from the one-dimensional example that you have to somehow combine a defect and a particle. Okay, and it turns out if you want to look at Dirac fermions in 2+1 dimension, you can take these vortices, attach them to a particle. The way you do that is you use a Chern-Simons term, and that turns out to be the dual theory for a Dirac fermion. Okay, so you can use the insights you get from 1D where things can be done exactly to sort of try to understand these dualities in higher dimensions. Okay, but maybe this is a good point to stop.